So far, we've just been dealing with single variables and objects. In this video, we'll start looking at some of the containers from the standard library that let us manage multiple objects at one time. C++ inherits plain arrays from C. The syntax for declaring an array looks like this. We've got the usual type, name, initializer structure, only now the variable name is followed by square brackets. These square brackets tell us that the variable will hold an array of ints. In this case, the size of the array is 3, as set by the number inside of the square brackets. With this array declared, we can access each of the elements like this. We put the name of the array followed by square brackets around the index of the element we want. The first element is at index 0, and the index counts up from there. In this example, we're asking for the second element using index 1, and the value we would get is 10. While these language-level arrays can sometimes be useful, it's usually easier to use one of the container types provided by the standard library. The first one we'll look at is std array. This container holds an array of elements where all the elements are the same type, and the size of the array is fixed at compile time. Here's what our array of 3 ints looks like as a std array. Let's take a moment to talk about this syntax. C++ has a feature called templates that lets us write generic code. In this case, std array is a templated class that uses 2 template parameters, the type of the elements and the size of the array. The actual code inside of std array is written without knowing the specific type it will end up containing, or how many there will be. When we declare an instance of std array and specify the template arguments, the compiler turns that generic code into fully specified code for our particular type and size. We'll look at how to write our own templates later. For now, we're just focused on using templated classes that other people have written for us. So with our new array declared, we can use the same syntax to access an element as we did with the language level array. But because this is now a proper object, there are also member functions we can call for more information about the array. The at function also gives us the value at a given index. However, this function checks that the index we're asking for is actually a valid index based on the array's size. Using the square bracket syntax, we could ask for the 4th element from this 3-element array, which would invoke undefined behavior. Using the at function instead, if we give an invalid index, an exception is thrown. Another useful function is the size function. This tells us how many elements are in the array. This may seem silly since the size of the array is known at compile time, but there are situations where being able to ask the array for its size is useful. So that's how we create a fixed size array, but that only works when we know how many elements we'll be dealing with at compile time. When we need a dynamically sized array, we use a different container called std_vector. Vectors only need to be templated based on the type of the element, since the size will change as we add and remove things. Vectors also support square bracket indexing, the at function, and the size function, just like std arrays. A useful function on vector that array doesn't have is pushback. Pushback adds a new element to the end of the vector. Looking through the documentation for std_vector on cppreference.com, we can see a handful of other useful functions. For example, there's empty, which checks if our container has no elements, or clear, which removes all the elements from the vector. There's also an erase function, and let's take a closer look at that. Looking at the documentation for this function, we can see it's expecting something called an iterator, which is a concept we haven't talked about yet. Iterators are a powerful abstraction that lets us write generic algorithms that work on many container types. An individual iterator represents a specific position inside a specific container. For example, we can get the iterator that represents the first element in our vector by calling its begin function. Its sibling function end gives us an iterator positioned 1 slot after the last element in the container. So if we wanted to erase the 3rd element from our vector, we could add 3 to the iterator that we got from begin. This takes that iterator representing the first position and moves it down to the 3rd position, then passes that shifted iterator to the erase function so it knows to erase the 3rd element. We'll be talking much more about iterators in later videos. There are many other container types available in the C++ library, such as linked lists, sets, and maps, but we don't have time to go through all of them in detail. If you're not familiar with these kinds of containers from another programming language, you may want to look through the documentation to see what they can do. In practice, std_vector is easily the most commonly used standard container in most C++ code. When paired with the standard library's algorithms, which we'll discuss later, std_vector is a very powerful tool.